Out there in the endless expanse of the cosmos, where stars flicker like distant campfires and galaxies swirl in silent majesty, the universe is whispering to us. Not with words, but with strange, elusive signals, bursts of energy, patterns of light, cryptic messages etched into the fabric of space itself. These aren't the echoes of supernovas or the hum of pulsars. These are signals we can't yet explain, mysterious pulses emerging from the depths of interstellar gas clouds, threading their way across the void to reach us. And what they're trying to say could rewrite everything we think we know about the universe. Imagine tuning a radio and suddenly catching a transmission from the unknown. That's what astronomers experience when these signals flicker onto their screens, cosmic whispers, enigmatic and tantalizing, hinting at forces or intelligences beyond our current understanding. Some of these signals repeat at precise intervals like clockwork ticking across light years. Others vanish as quickly as they appear, leaving scientists scrambling for answers. For decades, we've scanned the skies, searching for signs of life or phenomena that defy explanation. But these signals, these galactic enigmas, are different. They don't fit neatly into any known category. Are they the signatures of exotic cosmic events, ones we've never witnessed before? Could they be the byproducts of unimaginably vast structures lurking in the spaces between stars? Or just maybe, are they something far more profound, a deliberate signal, a beacon, a hello from another civilization reaching out across the dark? The possibilities are as thrilling as they are humbling. Every unexplained signal is a puzzle piece in a grand cosmic mystery, one that challenges our understanding of physics, of life, and of our place in the universe. That's why today we're diving deep into 25 of the most baffling signals ever detected from interstellar gas clouds, each one a story waiting to be unraveled. From the bizarre repeating pattern of one signal that has astronomers debating its origins for years, to the sudden, intense burst that seemed to come from nowhere, we'll explore the leading theories, the cutting-edge science, and the tantalizing clues that keep researchers up at night. This isn't just about astronomy, it's about the edges of human knowledge, the questions that push us to look further, to wonder harder. So settle in, because by the end of this journey, you'll never look at the night sky the same way again. The universe is speaking, and it's time we listened. One of the most infamous cosmic whispers ever recorded came not from a distant galaxy, but from our own Milky Way, a blip so extraordinary that the astronomer who discovered it scrawled, "Wow." In red ink right on the data printout, that single word gave the signal its legendary name, but the mystery behind it has haunted scientists for nearly 50 years. On August 15, 1977, Ohio State University's Big Ear radio telescope picked up an intense, narrowband burst of radiation, unlike anything astronomers had heard before. It blared at precisely 1420 MHz, the frequency scientists had long predicted an intelligent civilization might use to broadcast its existence before fading away after 72 seconds. And its origin, a seemingly unremarkable patch of sky in the constellation Sagittarius, where no star, pulsar, or known cosmic phenomenon should have been capable of producing such a focused, powerful transmission. The strangest part, it never repeated. Despite decades of follow-up scans, the WOW signal has remained stubbornly silent, deepening its enigma. Some believe it could have been an incredibly rare natural event, perhaps a comet's hydrogen cloud briefly reflecting sunlight in just the right way, though no known comet was in that region at the time. Others argue the signal's precision and frequency align eerily well with what we'd expect from an artificial beacon. If it was a message, was it a one-time call, a cosmic flare sent by accident, or worse, a distress signal we failed to answer? Then there's the unsettling possibility that we simply weren't listening the right way. The Big Ear telescope was stationary, scanning slices of the sky as Earth rotated. By the time astronomers rushed to train other instruments on Sagittarius, whatever sent that pulse had already gone quiet. What lingers today isn't just scientific curiosity, but the tantalizing weight of that red-inked exclamation on the printout. In a universe where unexplained signals are often dismissed as interference or equipment glitches, the WOW signal stands apart, too deliberate, too engineered to ignore. It forces us to confront the spine-tingling question: are we alone in the cosmos, or was that 72-second burst our first hello from the dark? The WOW signal's mystery took an unexpected turn in 2022 when a team of researchers proposed a provocative new explanation, one that reignited debates across the astronomy community. Their theory that the infamous burst wasn't extraterrestrial at all, but the fleeting reflection of sunlight off a passing comet's hydrogen cloud. Specifically, they pointed to two comets, 266P and 335P, which happened to be cruising through Sagittarius around the same time in 1977. Comets are known to carry vast envelopes of hydrogen gas, and if one had drifted through the telescope's field of view, it could have briefly amplified solar radiation at exactly 1420 MHz, mimicking an artificial signal. But here's where things get contentious. Critics quickly pounced on the theory's weak spots. For starters, comet positions in the 1970s weren't tracked with the precision we have today, meaning we can't say for certain those comets were even in the right patch of sky when the WOW signal hit. Worse, the signal's intensity was off the charts for a mere hydrogen reflection. As one astronomer put it, that's like blaming a candle for lighting up an entire stadium. The signal's narrowband frequency, too, seemed too finely tuned for a natural phenomenon. Comets don't emit radio waves in such a clean, focused way. Their signals are messy, scattered across frequencies. The debate cuts to the heart of how we interpret cosmic anomalies. On one side, skeptics argue that extraordinary claims, like contact with an alien civilization, require extraordinary evidence, and the comet theory, however shaky, at least keeps the explanation within known physics. But believers counter that dismissing the WOW signal too quickly risks overlooking something revolutionary. After all, history is littered with scientific breakthroughs initially dismissed as impossible. What if we're clinging too tightly to the familiar, ignoring the whisper of something truly new? Adding fuel to the fire, recent attempts to replicate the comet hypothesis have fallen flat. When researchers trained modern telescopes on similar comets, hoping to catch an identical burst, they got silence. No echoes, no repeats, just the void. It's a reminder that while the WOW signal might fade into legend, its legacy endures. Whether a cosmic fluke or a deliberate call, it remains a beacon not just in the stars, but in our collective imagination, pushing us to keep listening, to stay curious. Because out there in the dark, the next signal might not be a question mark at all. It might be an answer. If the WOW signal left us scratching our heads, the Lorimer Burst ripped up the astronomy playbook entirely. In 2007, a team led by astrophysicist Duncan Lorimer was sifting through decades-old radio telescope data when they stumbled upon something that shouldn't exist. A flash of cosmic energy so intense, so fleeting, it defied every known explanation. Lasting just 5 milliseconds, this burst packed more energy than the sun emits in 30 days, and it wasn't coming from some nearby star. The signal had traveled 3 billion light-years before slamming into Earth's telescopes, making it the first documented fast radio burst, or FRB. What makes the Lorimer Burst so baffling isn't just its staggering power, but its solitude. Unlike later FRBs that repeat like cosmic heartbeats, this one was a single, explosive shout into the void. Trying to study it is like investigating a firework that vanished before you even heard the bang. Scientists know it came from a distant dwarf galaxy, but pinpointing the exact source is like trying to find a needle in a universe-sized haystack. Was it the death scream of a collapsing neutron star, a cataclysmic collision between black holes, or something even stranger, something we haven't imagined yet? Theories abound, but here's the kicker: when astronomers race to train modern telescopes on that same patch of sky, hoping for a repeat performance, they heard nothing but silence. That one-off nature is what keeps physicists up at night. Without a second act, the Lorimer Burst remains a tantalizing outlier, a cosmic one-hit wonder that forces us to confront how little we truly understand about the universe's most violent, fleeting phenomena. Some argue these singular bursts could be the final acts of exotic celestial objects, like magnetars, neutron stars with magnetic fields so strong they warp the fabric of space itself. Others speculate they might be evidence of entirely new physics, perhaps the echoes of cosmic strings or quantum fluctuations in the early universe. What's undeniable is their scale. Even after thousands of FRBs have been detected since, the Lorimer Burst still stands out not just as a scientific milestone, but as a humbling reminder that the cosmos still holds surprises too big for our telescopes and maybe even our theories to contain. So while we wait for the next great burst to light up the sky, this 5-millisecond enigma lingers, proof that sometimes the universe's loudest statements are also its most fleeting. And somewhere out there, 3 billion light-years away, whatever caused it might already be gone, leaving behind only a whisper of radio waves and a mystery we're still desperate to solve. Just when scientists thought fast radio bursts couldn't get any stranger, the universe threw them a curveball, a signal that didn't just scream into the void once but kept screaming. In 2012, the Arecibo Observatory in Puerto Rico picked up something unprecedented, a burst from a tiny galaxy 3 billion light-years away that didn't just fade into silence. Days later, it erupted again, then again and again. Dubbed FRB 121102, this wasn't just another blip in the data, it was the first repeating fast radio burst ever discovered, shattering the assumption that these cosmic flashes were always one-time events. The implications were staggering. If singular bursts like the Lorimer explosion were cosmic car crashes, violent, chaotic, and unrepeatable, then FRB 121102 was more like a lighthouse pulsing with eerie regularity. Its bursts weren't identical. Some were sharp staccato snaps, others sprawling waves of energy, but they kept coming, sometimes days apart, sometimes in rapid-fire clusters. Astronomers suddenly faced a chilling question: what natural phenomenon could possibly choose to repeat? Magnetars quickly became the prime suspects. These city-sized neutron stars, spinning at dizzying speeds with magnetic fields 1 trillion times stronger than Earth's, are cosmic powder kegs. Some researchers theorize that FRB 121102 might be the death throes of a young magnetar, its crust cracking under unimaginable strain, releasing energy quakes that ripple across the universe. Others proposed even wilder ideas, like a magnetar orbiting a black hole, its magnetic field twisting into knots until it snaps like an overstretched rubber band, unleashing periodic bursts. But the plot thickened when scientists traced FRB 121102's location to a dwarf galaxy teeming with star formation, a cosmic nursery where magnetars are born. It fit until, of course, it didn't, because not all repeating FRBs come from such environments. Some emerge from quiet, aging galaxies, forcing astronomers to confront an uncomfortable truth. Maybe there isn't just one explanation. Maybe FRBs are like cosmic languages. Some are screams, some are whispers, and some, like 121102, are sentences we're still learning to decode. Then came the real mind bender. In 2019, another repeater, FRB 1822, was caught doing something unheard of. Its bursts followed a pattern. Every 16.35 days, it would fire off a cluster of signals, then go silent for 12 days. Like clockwork, suddenly, the idea of natural causes seemed almost too tidy. Could something or someone be scheduling these bursts? The scientific community bristled at the implication, but the question lingered like static in the air. After all, if you stumbled upon a radio tower in the desert pulsing at precise intervals, you wouldn't assume it was the wind, yet the magnetar theory refuses to die. Recent observations caught a Milky Way magnetar emitting an FRB-like burst, proving these stars can produce such signals. But here's the catch: our homegrown magnetar's burst was thousands of times weaker than the intergalactic monsters like 121102. It's like comparing a campfire to a supernova. So while magnetars might explain some FRBs, they can't explain all of them, especially not the repeaters with their cadences so precise they feel intentional. The debate rages on, but one thing's certain: every new FRB discovery peels back another layer of this cosmic onion, revealing just how little we know. Whether they're the cries of dying stars, the tremors of spacetime itself, or something beyond our imagination, these bursts are more than just scientific curiosities. They're breadcrumbs scattered across the universe, leading us toward truths we're only beginning to grasp. And out there, in the silence between the bursts, the cosmos waits patient, infinite, and full of secrets. While the search for extraterrestrial signals often focuses on galaxies billions of light-years away, one of the most electrifying false alarms in modern astronomy came from practically next door, our closest stellar neighbor, Proxima Centauri. In 2019, astronomers working with the Breakthrough Listen project detected something that sent shockwaves through the scientific community: a narrowband radio signal at 982 MHz, emanating from the very star system hosting an Earth-sized exoplanet in the habitable zone. Dubbed BLC-1, this tantalizing blip seemed to tick every box for an artificial transmission. It was laser-focused in frequency, drifting in a way that suggested a planetary origin, and most compellingly, it appeared only when telescopes were pointed at Proxima Centauri, not in the surrounding sky. For a brief, breathless moment, humanity dared to wonder, had we finally found them? Then came the crushing letdown. After months of painstaking analysis, researchers concluded BLC-1 was almost certainly human-made interference, likely a rogue radio signal bouncing off a satellite or a glitch in terrestrial equipment. The telltale clues: further scrutiny revealed the signal's frequency drift didn't perfectly match Proxima Centauri's motion, and its modulation bore an uncanny resemblance to known Earth-based technologies. Like a cosmic mirage, the dream of contact evaporated, yet beneath the disappointment, something curious lingers. BLC-1's narrowband frequency remains oddly precise for mere interference. Natural cosmic noise rarely carves such a clean, narrow spike in radio data. It's the electromagnetic equivalent of finding a perfectly straight line etched into a mountain. Even more perplexing, no one has definitively traced the signal to a specific human source, leaving a sliver of doubt. Could there be a minuscule chance, a fraction of a percent, that we dismissed an actual interstellar call too hastily? Critics argue that extraordinary claims demand extraordinary evidence, and BLC-1 simply didn't clear that bar. But supporters counter that our dismissal might say more about our biases than the data. History is littered with scientific breakthroughs initially mistaken for noise pulsars. For instance, were once labeled LGM signals, short for little green men. The lesson: while BLC-1 is probably earthly static, it's also a cautionary tale. As we refine our search for extraterrestrial intelligence, we're not just hunting for signals, we're learning to distinguish the universe's whispers from the echoes of our own civilization. And sometimes the hardest truth to accept is that the most exciting answer isn't always the right one. So while Proxima Centauri's mystery signal fades into the archives, its legacy endures. It's a reminder that every blip on the radar, whether a cosmic hello or a satellite's hiccup, holds value. Because in the grand search for connection, even the false alarms teach us how to listen better. And out there, in the quiet between the stars, the next signal might not be so easy to explain away. The BLC-1 false alarm wasn't just a fleeting disappointment, it became a turning point for how we hunt for extraterrestrial signals. Overnight, what seemed like a textbook case of intelligent contact revealed gaping holes in our methods, forcing the scientific community to wrestle with an uncomfortable truth. In a world saturated with human-made radio noise, distinguishing a cosmic hello from terrestrial static is harder than we ever imagined. The signal's fleeting promise triggered a seismic shift in SETI protocols, with researchers now implementing rigorous new safeguards to filter out earthly interference before jumping to interstellar conclusions. One major change, the three-step verification rule. Before any signal can be taken seriously as a candidate for extraterrestrial origin, it must now pass a gauntlet of tests. First, it must appear when the telescope is pointed at the target, but also disappear when aimed slightly away, ruling out ambient interference. Second, its frequency drift must precisely match the motion of the star system being observed, a telltale sign of planetary rotation or orbital dynamics. And third, the signal should lack any modulation patterns resembling human technology, from satellite downlinks to microwave ovens. Yes, kitchen appliances have famously mimicked alien broadcasts before. But the Proxima Centauri incident exposed an even deeper challenge, our own psychological biases. The moment BLC-1 appeared, excitement raced ahead of caution. It came from the nearest star with a potentially habitable planet, a detail so irresistibly tempting that even seasoned researchers felt its pull. This hopeful localization effect, as psychologists now call it, can warp objectivity, making us see what we want to see in the data. To combat this, modern SETI teams employ blind analysis techniques, where critical signal details are hidden during initial reviews to prevent unconscious bias from skewing interpretations. Meanwhile, Proxima Centauri remains under relentless surveillance. Though BLC-1 was likely a false alarm, astronomers continue to monitor the system with unprecedented precision, using arrays like the Very Large Telescope in Chile and the upcoming Square Kilometre Array, capable of detecting signals 10 times fainter than before. Why the obsession? Because hidden in the noise might be a second signal, one that passes all the new tests, and if it does, we'll be ready. Not with breathless speculation, but with cold, methodical verification. The legacy of BLC-1 isn't just a lesson in humility, it's a roadmap. Every dead end in science carves a clearer path forward, and this near miss taught us that the universe's greatest revelations might not announce themselves with fanfare. They could be whispers hiding in the static, waiting for us to refine our ears. So while Proxima Centauri's first signal turned out to be a cosmic prank, the next one might not be. And thanks to the protocols born from this false alarm, we're finally learning how to tell the difference. The mystery of SHGB-02+14 begins in 2003, when a team of astronomers sifting through SETI home data stumbled upon a signal so peculiar it defied easy explanation. Drifting out of the Pisces constellation, this faint radio whisper had two features that set pulses racing. First, its frequency wasn't static but glided smoothly across the spectrum, as if the source itself were in motion. Second, it originated from a patch of space so seemingly barren that scientists dubbed it a dead zone, a region devoid of stars, planets, or any known celestial objects capable of producing such a transmission. What made this signal truly bizarre was its behavior. Most natural cosmic radio sources, pulsars, quasars, the ambient hum of interstellar gas, emit across broad frequencies, creating messy, sprawling signatures. But SHGB-02+14 was surgical in its precision, a narrowband spike that seemed almost engineered. That precision, combined with its frequency drift, mirrored what scientists predict an alien broadcast might look like, a signal transmitted from a rotating planet, its motion causing the frequency to shift subtly, like the Doppler effect of a passing ambulance siren. Yet here's the catch: when researchers pointed telescopes back at Pisces, the signal had vanished, leaving behind only questions and a tantalizing data blip. The dead zone origin deepens the enigma. Normally, unexplained signals trace back to neutron stars, black hole jets, or other violent cosmic phenomena. But this patch of sky offered no such clues. No galaxies glittered in the background, no pulsars ticked in the void. It was, as one astronomer put it, like hearing a smoke alarm in an empty house. Some theorists suggest the signal might have been gravitationally lensed, bent, and amplified by an unseen object, making its true origin impossible to pinpoint. Others float darker possibilities. Could it have been a transient artifact from a long-dead civilization, its final broadcast finally reaching us eons after its senders perished? Skeptics, of course, have counter-arguments. The signal's drift, while unusual, isn't impossible for certain types of natural plasma emissions, and the dead zone might not be so dead after all. Faint, distant objects could lurk there, undetectable to our current telescopes. But the most striking critique is also the simplest. Without a repeat signal, SHGB 02+14 remains a cosmic mayfly. Here one moment, gone the next, leaving no evidence to scrutinize. Yet its legacy endures. This ghostly transmission forced astronomers to confront a humbling reality. Our maps of the universe are still riddled with blank spots, places where the unknown whispers. Whether a technical glitch, a natural fluke, or something more profound, SHGB 02+14 serves as a reminder that the cosmos refuses to be neatly catalogued. And somewhere in the silence between the stars, other signals might be waiting, not in the places we expect to find them, but in the voids we've overlooked. In 2016, a pair of Canadian astronomers dropped a bombshell that sent ripples through the scientific community. 234 stars, scattered across the Milky Way, appeared to be pulsing in near-perfect synchronization. The discovery, published in the journal Publications of the Astronomical Society of the Pacific, wasn't just unusual, it was borderline unbelievable. The stars, all sun-like in size and temperature, emitted rapid, rhythmic bursts of light flashes so precise they seemed orchestrated. The researchers Ermanno Bora and Eric Trottier didn't outright claim they'd found aliens, but their paper floated a tantalizing possibility. What if these pulses weren't natural at all, but laser signals from advanced civilizations deliberately targeting Earth? The idea wasn't entirely out of left field. Bora had previously theorized that extraterrestrial societies might use high-powered lasers for interstellar communication, modulating their beams to create detectable patterns in a star's light spectrum. And here, in real data from the Sloan Digital Sky Survey, were spikes matching his predictions: narrow, periodic dips and peaks in the star's spectral lines, all clustered around the same frequency. The odds of this happening by chance, roughly 1 in 10,000, the study claimed. Suddenly, the cosmos seemed alive with flickering beacons, as if someone or something had rigged the galaxy's stars to blink in unison. But the euphoria was short-lived. Within months, a chorus of skeptics dismantled the alien laser hypothesis piece by piece. Independent analyzers revealed that the pulses weren't pulses at all, just mundane stellar vibrations, the natural throbbing of sun-like stars as their surfaces heated and cooled. These pulsations, known as granulation noise, had been documented for decades. The supposed synchronicity, a statistical fluke amplified by the sheer volume of stars surveyed. Even the study's 1 in 10,000 probability came under fire. Critics argued the team had cherry-picked data, retroactively applying filters until a pattern emerged. By the time the peer-reviewed debunkings piled up, the 234-star anomaly had fizzled into textbook confirmation bias, a case of seeing what you want to see in the noise. Yet the episode left an indelible mark on SETI research. For all its flaws, Bora and Trottier's work forced astronomers to grapple with a provocative question. If aliens were trying to communicate via lasers, how would we tell the difference between a signal and stellar noise? Their methodology, though flawed, pioneered new ways to scan starlight for artificial modulation, techniques now refined and incorporated into modern searches. More importantly, the controversy highlighted a cultural rift in the scientific community. To some, chasing such anomalies was a reckless gamble, a distraction from serious astronomy. To others, it was precisely this kind of audacious thinking that could shatter paradigms. After all, history's greatest discoveries often begin as heresies. The 234-star anomaly may have been debunked, but its legacy lingers not as evidence of alien contact, but as a cautionary tale and a catalyst. It reminds us that the line between groundbreaking discovery and wishful thinking is razor-thin, and that the universe's greatest mysteries often hide in the data we've already collected, waiting for someone to ask the right question. So while those stars weren't signaling us, their story still carries a message. Sometimes the most valuable thing we find in the cosmos isn't a beacon from the dark, it's a mirror, reflecting back our own hopes, biases, and unyielding hunger for connection. In 2015, a Russian radio telescope scanning the cosmos detected something that set the astronomy world ablaze. A powerful, unexplained signal emanating from a star strikingly similar to our own Sun. Designated HD 164595, this star sits 94 light-years away in the constellation Hercules, and for a brief moment, it emitted a radio burst so peculiar that even seasoned scientists entertained the spine-tingling possibility. Was this our first glimpse of an advanced civilization's technology? The signal, detected by the Ratan 600 telescope in Zelenchikskaya, was a sharp, narrowband pulse centered at 11 GHz, a frequency with no known natural explanation. What made it even more intriguing was its strength. If the transmission was artificial, and if it had been broadcast omnidirectionally into space, the energy required would dwarf humanity's total power output. Calculations suggested it would demand the equivalent of 100 trillion watts, enough to power our entire planet thousands of times over. That kind of energy expenditure hinted at something staggering, a civilization capable of harnessing their star's full power, a theoretical Type 2 on the Kardashev scale. Of course, the scientific community reacted with a mix of excitement and skepticism. The first hurdle was the signal's fleeting nature. It appeared once for just 2 seconds and never repeated. Transient cosmic phenomena like hyperflares from magnetically active stars could theoretically produce such a burst. HD 164595, while Sun-like, is known to be slightly older and more metal-rich than our star, factors that might influence stellar behavior in ways we don't yet fully understand. Could it have unleashed a freak, ultra-powerful flare in a frequency range we've never observed before? But the plot thickened when researchers considered an alternative explanation. What if the signal wasn't meant for us? If an advanced civilization were beaming energy for their own purposes, say, powering interstellar probes or communicating with colonies, Earth might have simply passed through the path of a narrowly focused transmission. Like stumbling into the beam of a cosmic flashlight, we'd catch only a fleeting glimpse before it swept past. This leakage scenario would drastically reduce the energy requirements, making the signal plausible as a byproduct of alien engineering rather than a deliberate hello. The debate reached a fever pitch when astronomers scrambled to train other telescopes like the SETI Institute's Allen Telescope array on HD 164595, hoping for a repeat. Silence followed, no second signal, no corroborating data. Without further evidence, the hypothesis began to crumble. Critics pointed out that terrestrial interference, perhaps from a passing satellite or military radar, could have mimicked the signal's profile. Others noted that Ratan 600's wide field of view made pinpointing the exact source tricky. The burst might not have originated from the star at all, but from some background object in the same direction. Yet the HD 164595 incident left an indelible mark. It forced astronomers to confront the gaps in our understanding of stellar activity, especially in understudied frequency ranges. It also highlighted the agonizing challenges of SETI, distinguishing a needle of possibility in a haystack of cosmic noise and human-made interference. Most of all, it served as a reminder that the universe is vast, nuanced, and full of phenomena we've yet to categorize, whether natural or otherwise. So while HD 164595 signal remains unexplained, its legacy endures. It's a case study in balancing open-minded curiosity with rigorous skepticism, a lesson that the most tantalizing cosmic whispers often leave us with more questions than answers. And somewhere out there, 94 light-years away, a star continues to shine, its secrets still hidden, its mysteries still unresolved, waiting for the next time it decides to speak. In the summer of 2017, a quiet red dwarf star 12 light-years away suddenly made headlines, not for its planets or flares, but for a radio signal so perplexing that astronomers spent months debating whether they'd stumbled upon cosmic static or something far more intriguing. Ross 128, a dim, cool star in the constellation Virgo, had been under routine observation by the Arecibo Observatory when it unleashed a burst unlike anything in the telescope's decades of operation. The signal was narrowband, centered around 4 to 5 GHz, a range with no known natural astrophysical source, and it pulsed with a pattern that mirrored the cadence of human-made transmissions. For 10 heart-pounding minutes, scientists stared at data that seemed to whisper, "This isn't just noise." The immediate suspicion, of course, was earthly interference. Satellites constantly crisscross the sky, and their radio chatter often bleeds into astronomical observations. But Ross 128's signal had a smoking gun. Its frequency drifted, subtly shifting over time in a way that matched the star's motion relative to Earth. That drift is a telltale fingerprint of celestial origin, like hearing a train whistle change pitch as it speeds past. If the signal came from a satellite, it wouldn't drift that way unless the satellite itself were accelerating inexplicably. The more researchers ruled out, the more the mystery deepened. Then came the solar flare theory. Red dwarfs like Ross 128 are notorious for their violent tantrums, capable of erupting with flares hundreds of times more powerful than our suns. Could an extreme stellar outburst have masqueraded as an artificial signal? Some astronomers argued yes, pointing to rare, coherent radio bursts from flares, a phenomenon where magnetic energy organizes radio waves into narrowband spikes. But there was a problem. Ross 128 was quiet that day. No X-rays, no ultraviolet spikes, none of the usual fireworks accompanying a flare. It was like hearing thunder without seeing lightning. The debate took a surreal turn when researchers noticed the signal structure bore an uncanny resemblance to frequency modulation used in human communication. The pulses weren't random, they clustered in a way that felt organized, almost as if something or someone had encoded information into the waves. Even skeptics admitted the parallels were eerie. Yet without a repeat signal, the scientific community hit a wall. Was this a never-before-seen stellar phenomenon, a glitch in Arecibo's aging hardware, or the faint echo of a civilization we've yet to understand? In the end, the most plausible explanation turned out to be the most mundane sort of. Further analysis suggested the signal likely came not from the star itself, but from one or more geostationary satellites drifting through Arecibo's field of view. Their signals, reflected off orbital debris or atmospheric layers, could theoretically mimic the frequency drift of a distant star. It was a cosmic game of telephone, with human technology whispering lies into the ears of our telescopes. Yet Ross 128's enigma lingers. The satellite hypothesis, while persuasive, hasn't been proven conclusively, and the star's flare-quiet nature during the signal's arrival still nags at researchers. Perhaps the greatest lesson here isn't about aliens or stellar physics, but about humility. The universe is a hall of mirrors reflecting back our assumptions, our biases, and the limits of our tools. Ross 128 signal may have been a false alarm, but it taught us something invaluable. In the hunt for cosmic mysteries, sometimes the most ordinary explanations are the hardest to accept and the most important to verify. In 2008, a ripple of excitement spread through the astronomy community when an anonymous team of researchers posted an electrifying claim on an online preprint server. They'd detected a radio signal from the Andromeda Galaxy M31, our nearest galactic neighbor, that defied every known natural explanation. The signal, they asserted, bore the hallmarks of artificial origin, a narrowband transmission pulsing at precisely 1.4 GHz, a frequency cluttered with human-made interference on Earth but disturbingly pristine when emanating from 2.5 million light-years away. The implications were staggering. If legitimate, this wasn't just a breakthrough, it was the holy grail of SETI, proof that intelligence existed beyond our galaxy. Almost immediately, skepticism rained down. The paper lacked authorship, institutional affiliation, or peer review red flags in the scientific world. Critics dissected the signal's metadata, pointing out inconsistencies in its Doppler shift, which didn't align with Andromeda's well-documented motion. Then came the bombshell. The signal's digital fingerprints matched those of a known software glitch in certain radio telescopes, an artifact created when terrestrial interference bled into raw data. Within weeks, the astronomical consensus was clear. The Andromeda signal was a phantom, a cosmic mirage born of wishful thinking and technical hiccups. Yet the story refused to die. In the shadowy corners of the internet, conspiracy theorists latched onto the signal's enigmatic origins. Why, they asked, would researchers risk professional ruin to fabricate such a claim anonymously? Why did portions of the data resist easy debunking, showing patterns that even skeptics admitted were oddly structured? The whispers grew. Was this a deliberate leak, a breadcrumb dropped by insiders forced to bury the truth? Fueling the fire were declassified government documents mentioning unexplained, extragalactic radio anomalies, though none specifically tied to M31. The signal's resurgence in fringe circles became a case study in how science grapples with ambiguity and how easily gaps in knowledge become fertile ground for myth. Scientists, meanwhile, turned the episode into a cautionary tale. The Andromeda signal's rise and fall underscored the importance of transparency in SETI research, where public fascination often outpaces evidence. It also highlighted a deeper, almost philosophical tension. In a universe as vast as ours, where signals can take millions of years to reach us, how do we distinguish between a message and a mirage? The answer, for now, lies in rigor and patience, because while the 2008 signal faded into infamy, Andromeda itself still looms large in our telescopes, a silent giant holding secrets we've only begun to untangle. And if it ever does speak, we'll be listening not with desperation, but with the disciplined curiosity that separates science from speculation. Among the thousands of stars monitored by NASA's Kepler telescope, one stood out not for its stability but for its chaos. Kepler 438, a red dwarf 500 light-years away in the constellation Lyra, should have been just another unremarkable flicker in the data. But in 2015, astronomers noticed something bizarre. Its light curve was wild. Unlike the predictable dips caused by orbiting planets, this star's brightness plummeted in erratic, jagged spikes, as if someone were flicking a cosmic light switch at random. At times, its luminosity dropped by a staggering 40%, far more than any known planet could block. The readings looked less like an exoplanet transit and more like a strobe light malfunction in deep space. The strangest part, these dips weren't periodic. They came in irregular clusters, sometimes days apart, sometimes months, with no discernible rhythm. Naturally, minds raced to wild possibilities. Could this be evidence of a megastructure, a Dyson sphere under construction, its skeletal framework sporadically blotting out the star's light as panels aligned? The hypothesis wasn't entirely far-fetched. In theory, an advanced civilization harvesting a star's energy might build vast orbital arrays, and their incomplete construction could explain the chaotic shadow patterns. For a thrilling moment, Kepler 438 became the poster child for technosignature searches, a real-world Tabby star scenario with even weirder data. But the universe rarely serves up easy answers. Skeptics quickly proposed alternative explanations, starting with swarms of comets. If Kepler 438 were surrounded by millions of icy fragments, a debris field far denser than our own solar system's Oort cloud, their uneven distribution could create the star's jagged dimming pattern. Another camp pointed to the star itself. Red dwarfs are notorious for violent flares and sunspot activity. Perhaps Kepler 438's surface was marred by titanic magnetic storms, distorting its light output in ways we'd never observed before. Then there was the simplest explanation of all: glitches. Kepler's instruments, though remarkably precise, weren't infallible. Cosmic rays, thermal fluctuations, or even minor software errors could theoretically mimic exotic astrophysical phenomena. The debate reached a crescendo when follow-up observations failed to detect any infrared excess, a key signature of a Dyson sphere, which would theoretically irradiate absorbed starlight as heat. Without that telltale warmth, the megastructure hypothesis crumbled. Yet the comet and stellar activity theories didn't quite fit either. No known natural phenomenon could fully account for the star's extreme aperiodic dimming. Kepler 438's mystery endures as a reminder of how much we still don't understand about stellar behavior and how easily our imaginations outpace reality. The lesson here isn't just about one erratic star. It's about the delicate dance between curiosity and skepticism that defines modern astronomy. Every unexplained signal invites two responses: the thrilling, what if, and the grounding, but wait. Kepler 438's strobe-like flickers may not be aliens, but they're not nothing either. They're a puzzle waiting for the right key, one that might unlock not just the secrets of this one star, but entirely new chapters in astrophysics. Until then, the data keeps blinking back at us, silent but insistent, like a Morse code we haven't learned to read. If Kepler 438's flickers were baffling, KIC 8462852, better known as Tabby's star, took cosmic mystery to another level. Discovered in 2015 by citizen scientists sifting through Kepler Space Telescope data, this unassuming star in the constellation Cygnus quickly became infamous for behavior so strange it defied every textbook explanation. Unlike planets, which cause predictable periodic dips in starlight as they transit, Tabby's star dimmed erratically, sometimes by as much as 22%, a staggering drop no known celestial object could explain. The fluctuations weren't just deep, they were irregular with no discernible pattern. One week, the star's light would plummet dramatically. Months later, it might dip again, but this time in a jagged, uneven curve that looked more like a heartbeat flatlining than a planet's clean shadow. Theories erupted like supernova. At the forefront was the tantalizing and controversial megastructure hypothesis. Astronomer Jason Wright and others speculated that the star's light might be partially blocked by an artificial construction like a Dyson swarm, a vast array of energy-harvesting satellites orbiting the star. The idea wasn't pure science fiction. If an advanced civilization had embarked on such a project, the incomplete or uneven arrangement of these structures could easily account for the star's bizarre dimming. The internet predictably exploded. Tabby's star became a media sensation, dubbed the most mysterious star in the universe, with headlines breathlessly asking, "Have we found aliens?" But science thrives on skepticism, and alternative explanations soon emerged. The most compelling involved cosmic dust, but not just any dust. Researchers noted that the star's infrared signature didn't match what you'd expect from a solid megastructure. Instead, the dimming seemed wavelength-dependent, meaning shorter wavelengths of light were blocked more than longer ones. That's a classic fingerprint of fine particles, like the kind found in comet debris or interstellar dust clouds. One study proposed a shattered planet or moon, its fragments creating a sprawling, uneven ring system that would intermittently obscure the star's light. Others suggested a family of giant comets, hundreds of times larger than Halley's Comet, drifting in chaotic orbits, yet even these theories left gaps. For dust to explain the deepest dimming events, there'd need to be an implausibly vast amount of it, more than our solar system has ever contained, and the star's long-term fading, observed over a century of historical data, added another layer of intrigue. Tabby's star wasn't just flickering, it was slowly darkening, as if something was steadily accumulating between it and us. Natural explanations strained under the weight of these observations, leaving astronomers with a maddening truth. Tabby's star didn't fit neatly into any box, artificial or otherwise. The controversy reached a turning point in 2018 when new observations revealed the star's dimming was color-sensitive, a detail that all but ruled out opaque megastructures. Dust, it seemed, was the culprit after all, but this wasn't a tidy resolution. The dust's origin remained a puzzle. Was it the aftermath of a colossal planetary collision, the remnants of a disintegrating comet swarm, or something even stranger, like interstellar material being gravitationally funneled into the star's vicinity? Years later, Tabby's star still refuses to surrender its secrets. It's become a symbol of how science wrestles with the unknown, a reminder that the universe often serves up mysteries faster than we can solve them. The megastructure hypothesis, though largely set aside, left an indelible mark on astronomy, proving that even fringe ideas can push research forward. Today, the star remains under intense scrutiny, its every flicker a potential clue in a cosmic detective story with no final chapter. What makes Tabby's star so compelling isn't just the lingering questions, but the way it challenges our assumptions. In a universe teeming with predictable phenomena, anomalies like this force us to rethink the boundaries of the possible. Whether the answer ultimately lies in dust, debris, or something beyond our current understanding, one thing's certain: the cosmos loves a good mystery. And Tabby's star, with its enigmatic dimming and defiant silence, might just be its masterpiece. The James Webb Space Telescope has finally turned its powerful infrared eye toward Tabby's star, and the results are reshaping the debate in ways no one expected. In 2023, fresh data from JWST delivered a bombshell. The star's bizarre dimming wasn't caused by alien megastructures after all, at least not the kind we imagined. Instead, the telescope's sensitive instruments detected a wavelength-dependent signature that screams dust, not metal. The telltale clue: when Tabby's star dimmed, shorter wavelengths of light, like blue and ultraviolet, were blocked far more dramatically than longer, infrared wavelengths. That's exactly what you'd see if fine particles were filtering the starlight, scattering shorter frequencies like a cosmic sieve. But here's where the plot thickens. This isn't ordinary interstellar dust. JWST's spectral analysis revealed the particles are asymmetrically distributed, clumping in strange, uneven formations around the star. One leading theory suggests a cataclysmic collision, perhaps two icy moons or dwarf planets smashing apart, their debris field swirling into a lopsided cloud that intermittently eclipses the star from our vantage point. Another possibility: a family of giant exocomets trailing vast plumes of dust as they disintegrate under the star's gravitational pull. The data even hints at microscopic grains smaller than cigarette smoke, which could explain the extreme dimming without requiring unimaginable amounts of material. Yet the megastructure camp hasn't surrendered entirely. Some researchers point out that advanced civilizations might use dust deliberately as a coolant or construction material, meaning JWST's findings don't entirely rule out intelligence. It's a long shot, but it underscores how Tabby's star continues to defy easy categorization. Even now, with dust as the prime suspect, critical questions linger. Why is the dimming so erratic? What process could scatter debris in such chaotic arrangements? And why does historical data show the star has been gradually fading for over a century? What makes these JWST observations so groundbreaking isn't just the answers they provide, but the new mysteries they've unearthed. For the first time, we're not just guessing at the nature of Tabby's star's shadows, we're seeing them in unprecedented detail. And with every new dataset, the line between the improbable and the impossible blurs just a little more. One thing's certain, the universe loves a good curveball, and Tabby's star is still pitching. In the vast cosmic ocean of unexplained signals, few have sparked as much ethical controversy as the deliberate message beamed toward GJ273b, a potentially habitable exoplanet just 12 light-years away in the constellation Canis Minor. The story begins in 2017, when scientists from METI International Messaging Extraterrestrial Intelligence took the provocative step of actively transmitting a signal toward this alien world, rather than passively listening for incoming messages. The transmission, sent from a radar antenna in Norway, contained mathematical and scientific tutorials, musical compositions, even a cosmic hello encoded in binary pulses. It was humanity's modern-day equivalent of throwing a message in a bottle into the galactic tides, only this bottle was a high-powered radio beacon announcing our presence to the universe. The backlash was immediate and fierce. Critics, including towering figures like Stephen Hawking, warned that actively signaling advanced civilizations could be catastrophically naive. Hawking likened it to Native Americans shouting into the unknown just before Columbus arrived, a cautionary tale about inviting contact with potentially predatory explorers. Even some SETI researchers distanced themselves, arguing that meta-unilateral action bypassed global consensus on whether humanity should be broadcasting its coordinates to the cosmos. The debate cuts to the core of scientific ethics. Do we have the right to speak for an entire planet, risking consequences we can't foresee? Then came the twist that no one expected. In 2019, 2 years after the initial transmission, the exact time it would take for a signal to reach GJ273b and, if answered immediately, return to Earth, our team at the Instituto de Astrofísica de Canarias detected something peculiar. A series of pulses echoing the original message's frequency and timing flickered onto their equipment. The implications were staggering. Had we just received our first cosmic reply? Skeptics pounced. The response lacked the hallmarks of an engineered signal. Its structure was messy, its content indecipherable. More damningly, the pulses originated not from GJ273b's precise location, but from a patch of sky nearby, likely the emission of a distant quasar or neutron star. The timing, while poetic, was almost certainly coincidence. The universe is vast enough that random radio noise could mimic a reply. Yet for true believers, the parallel was too eerie to ignore. What if the signal was intentional, but distorted by interstellar medium or relayed via an intermediary probe? The absence of proof isn't proof of absence, they argued, a mantra that fuels many ongoing transmissions despite the controversy. This episode leaves us with more than just scientific questions. It forces a reckoning with humanity's role in the cosmos. Are we the eager newcomers shouting into the dark, or reckless children playing with forces beyond our understanding? GJ273b's silence, or perhaps its cryptic static, offers no easy answers. But one thing's clear: as our signals streak across the void, we're no longer just observers of the universe's mysteries. We've become active participants, for better or worse, and somewhere out there, 12 light-years away, a potentially habitable world orbits its red dwarf sun, unaware, perhaps, that it's now entangled in humanity's greatest experiment. The question isn't just whether they'll respond, it's whether we're ready for what they might say. Of all the cosmic oddities humanity has encountered, few have ignited debates like the interstellar visitor known as Oumuamua. This cigar-shaped object, first detected in 2017, barreled through our solar system with a trajectory so peculiar it defied classification. Unlike comets or asteroids, Oumuamua exhibited a slight but unmistakable acceleration, one that couldn't be explained by gravity alone. The kicker: it left no visible trail of gas or dust, the usual fingerprints of a comet's thrust. This wasn't just a rock tumbling through space. It was behaving as if something else, something unseen, was pushing it. Harvard astrophysicist Avi Loeb famously floated a radical explanation: Oumuamua could be artificial. Its flattened shape, roughly 10 times longer than it was wide, resembled theoretical designs for interstellar light sails, craft propelled by starlight itself. The acceleration, Loeb argued, might have been caused by radiation pressure from the sun, a natural force that could also power human-made solar sails. Even more provocative was the object's unusually bright reflectivity, suggesting a surface potentially polished or metallic. For a fleeting moment, the possibility hung in the air: were we looking at debris from an alien civilization or even a derelict probe? Skeptics, of course, fired back. They proposed that Oumuamua's acceleration could stem from outgassing hidden jets of hydrogen or other gases too faint for telescopes to detect. Others suggested it might be a shard of frozen nitrogen sheared off a Pluto-like exoplanet, its gradual vaporization explaining the thrust. But critics pointed out flaws. Hydrogen outgassing would have altered Oumuamua's spin, which it didn't exhibit, and nitrogen ice wouldn't account for the object's reflectivity or bizarre shape. The debate soon spilled beyond academia, becoming a cultural flashpoint about how far scientists should go in entertaining extraterrestrial hypotheses. What makes Oumuamua's mystery so enduring isn't just the unanswered questions, but what it implies about interstellar space. If this object was natural, it represents a wholly new class of celestial body, one that challenges our understanding of planetary formation. If it wasn't, the implications are even more profound. Either way, its fleeting visit forced us to confront an unsettling truth. The universe might be littered with objects we don't yet know how to categorize, some of which could be sending signals we're ill-equipped to detect. Consider this: Oumuamua tumbled past Earth silently, but what if similar objects emitted faint radio pulses or other signatures as they traversed the cosmos? Our telescopes weren't trained on it until it was already leaving. Future visitors might carry subtler clues, ones we'd miss without the right tools. That's why Loeb and others advocate for interstellar archaeology, a dedicated effort to scan incoming objects for anomalies, whether natural or engineered. Because the next Oumuamua might not just drift by unnoticed, it might be trying to tell us something. The stakes go beyond one strange object. Oumuamua's legacy is a paradigm shift in how we view the cosmos. It's a reminder that the universe doesn't neatly conform to our expectations, and that the line between groundbreaking discovery and heresy is often thinner than we admit. Whether a cosmic iceberg or a fragment of alien technology, its true nature remains unresolved. But one thing's certain: the next time an interstellar visitor streaks through our backyard, we'll be watching not just with curiosity, but with the humbling awareness that some mysteries refuse to stay quiet. On August 27, 1998, Earth's orbital telescopes caught an explosion in deep space, but not just any explosion. The gamma-ray burst, catalogued as Vela Jr., detonated with such precision that its energy signature didn't just spike and fade. It rang like a bell struck in the vacuum of space. Lasting nearly 5 minutes, the burst pulsed with a rhythmic rise and fall of gamma rays, an oscillation so regular that astrophysicists initially thought their instruments were glitching. Yet the data didn't lie. Something out there, roughly 800 light-years away in the constellation Vela, had shuddered with unnatural symmetry, and to this day no one's entirely sure what it was. The leading theory points to neutron stars, those SETI-sized corpses of dead suns. spinning at dizzying speeds with gravity so intense a teaspoon of their material would weigh 1 billion tons on Earth. When these ultra-dense objects undergo starquakes, fractures in their crystalline crusts, the resulting vibrations can theoretically produce gamma-ray oscillations. Vela JR's ringing pattern fits except for one glaring inconsistency. Most neutron starquakes produce messy, chaotic tremors. This signal was clean, almost musical in its precision, with harmonics that mirrored the resonant frequencies of a perfectly balanced sphere. It's the difference between a wine glass shattering and one humming a pure, sustained note when tapped. Then there's the location. Vela JR erupted near a sprawling interstellar gas cloud, a region where conventional astrophysics struggles to explain how a neutron star could exist undetected. Gamma-ray bursts typically originate from galaxies billions of light-years away, not our cosmic backyard. The proximity raises unsettling questions. Was this a natural event closer than we thought, or something else entirely, a signal amplified or redirected by the gas cloud itself? Skeptics argue the burst's energy profile aligns with a soft gamma repeater, a known class of neutron stars prone to violent outbursts. But believers counter that no known repeater has ever produced such a finely tuned oscillation, nor at this distance. The most radical hypothesis, Vela JR, wasn't natural at all. The signal's symmetry and energy dispersion bear eerie similarities to theoretical models of antimatter annihilation, a process that, if harnessed, could propel spacecraft at relativistic speeds. Could the burst have been the exhaust plume of an advanced propulsion system, briefly igniting as it traversed the gas cloud? It's a fringe idea, but not without precedent. Decades earlier, physicist Freeman Dyson speculated that sufficiently advanced civilizations might leave detectable energy signatures in gamma spectra, whether intentionally or as byproducts of their technology. Yet for all the speculation, Vela JR remains an enigma. The event never repeated, leaving astronomers with a single, tantalizing dataset to scrutinize. Modern telescopes, armed with AI-driven analysis tools, continue to comb through archived readings, searching for clues that might have been missed. What lingers isn't just scientific curiosity, but the humbling realization that even in our own galactic neighborhood, the universe can still surprise us. Whether a neutron star's cry or something far stranger, Vela JR's ringing echo serves as a cosmic reminder. Sometimes the most profound mysteries aren't in the distant cosmos but right next door, waiting silently for us to listen. The universe isn't just expanding, it's dragging entire galaxy clusters with it in a phenomenon so bizarre, scientists still struggle to explain it. Known as dark flow, this mysterious motion was first detected in 2008, when astronomers noticed hundreds of galaxy clusters drifting in the same direction at inexplicable speeds, as if pulled by some unseen force beyond the observable universe. But here's where things get even stranger. Recent radio telescope surveys have picked up faint, anomalous emissions, whispers of energy aligning eerily with this cosmic current. These signals don't match any known astrophysical source. They're not quasars, not pulsars, not the ambient crackle of the cosmic microwave background. Instead, they pulse with a peculiar cadence clustered along the dark flow's trajectory like breadcrumbs leading to, well, something we can't yet see. The leading theory, these radio waves could be the faint echo of another universe. In multiverse models, our cosmos might be one bubble among countless others, each with its own physical laws. If a neighboring universe brushed against ours long ago, its gravitational tug could explain both the dark flow and these lingering radio echoes, like ripples from a pebble tossed into a pond we can't see. Alternatively, the signals might stem from quantum vacuum noise, the seething energy of empty space itself. At the universe's largest scales, where spacetime stretches thin, this background hum could amplify into detectable waves, twisted into coherence by the dark flow's pull. But skeptics argue the emissions could be artifacts of our own cosmic blind spots. The region emitting these waves lies behind the Milky Way's galactic plane, an area notoriously difficult to observe due to dust and stellar interference. Could the signals simply be noise distorted by our limited vantage point? Perhaps, yet the timing is uncanny. Multiple independent telescopes, from the Planck satellite to ground-based arrays, have detected similar anomalies along the dark flow's path, ruling out isolated glitches. The most tantalizing possibility remains the most speculative, that these radio waves are a signature of something beyond physics as we know it. If dark flow is truly the gravitational imprint of other universes, these signals might be our first indirect evidence of a reality vaster than we ever imagined. Or they could be something else entirely, a cosmic phenomenon we haven't even named yet, lurking at the edge of comprehension. For now, the dark flow's radio whispers remain an open case, a puzzle with pieces scattered across the cosmos. Every new observation peels back another layer, revealing just how little we understand about the forces shaping our universe's grandest motions. And as telescopes grow more sensitive, one thing's certain: the deeper we listen, the more the universe surprises us. Whether a multiverse's echo or the murmur of quantum foam, these signals remind us that the cosmos is far stranger, far richer than we've dared to dream. Somewhere in the vast stretch between the constellations Hercules and Corona Borealis, the cosmos is humming, not with the violent crackle of a supernova or the rhythmic pulse of a neutron star, but with something far stranger, a deep, persistent radio drone, so low in frequency it skirts the edge of what our telescopes can detect. First picked up in the early 2000s and then forgotten for years, this enigmatic signal, dubbed the Hercules Corona hum, re-emerged in 2020 with a vengeance, stronger and clearer than ever before. Unlike the fleeting bursts that dominate SETI research, this hum lingers, a cosmic bass note thrumming through the void with eerie consistency. The signal's origin lies in a sprawling interstellar gas cloud, a region so thick with ionized particles it practically crackles with ambient energy. Yet even in this chaotic environment, the hum stands out. Its frequency, hovering around 160 MHz, is too steady for most natural processes. Turbulent plasma, the usual suspect for cosmic radio noise, produces messy, broadband static, not this narrow, unwavering tone. That precision has scientists divided. One camp argues the hum could be the resonant vibration of primordial black holes, hypothetical relics from the universe's infancy. These ancient objects, if they exist, might oscillate as they evaporate, emitting low-frequency waves like a tuning fork struck at the dawn of time. The rival theory points to plasma itself, but not the usual chaotic swirls. Under specific conditions, vast clouds of ionized gas can enter a state called Langmuir oscillations, where electrons vibrate in unison, producing coherent radio waves. The catch: such synchronization requires temperatures and densities unlike anything we've observed in the Hercules Corona region. Unless, of course, we're missing a key piece of the puzzle, like an unseen magnetic field threading the gas, orchestrating the chaos into order. Rediscovering the hum in 2020 only deepened the debate. Modern radio arrays, far more sensitive than their predecessors, confirmed the signal wasn't an artifact of old equipment. Even more baffling, the hum's intensity fluctuates over months, not randomly but in a slow, cyclical pattern, as if something out there is breathing. Could this be the heartbeat of a hidden celestial object, or the echo of a mechanism we don't yet understand? What makes the Hercules Corona hum so compelling isn't just its mystery, but its persistence. While other signals flash and fade, this one endures, a whisper from the dark that refuses to be ignored. Whether the murmur of dying black holes or the song of disciplined plasma, it's a reminder that the universe communicates in more ways than we've dreamed. And sometimes the most profound messages aren't shouts or screams, but the quiet, steady hum of something vast and unknown, waiting for us to decipher its tune. Deep in the heart of the Triangulum Galaxy, 28 million light-years from Earth, something strange is repeating itself with clockwork precision. A signal that arrives every 16 days like a cosmic metronome echoing across the void. Discovered in 2020 by the CHIME radio telescope array, this pulse from Messier 33 defies simple explanation. Unlike the chaotic bursts of magnetars or the erratic flickers of quasars, the triangulum echo follows a pattern so precise it feels almost engineered. For 4 days it blares relentlessly, then falls silent for 12, only to return right on schedule, as if set by some unseen celestial timer. Astronomers first assumed they'd found an exotic pulsar, a spinning neutron star sweeping beams of radiation across space like a lighthouse. But pulsars slow down over time, their rhythms decaying as they lose energy. The triangulum echo's timing, however, remains flawlessly stable, its 16-day cycle unvarying across years of observation. That consistency led researchers down a rabbit hole of alternative explanations. One compelling theory involves a pulsar wind nebula, a turbulent bubble of particles blown off by a neutron star. If this pulsar were orbiting a companion star, its winds could collide with the companion's own outflow, creating shock waves that emit radio bursts at regular intervals. The math nearly fits. A 16-day orbital period isn't unheard of in binary systems. Yet even this elegant model strains under scrutiny. The signal's spectral fingerprint doesn't quite match known pulsar wind interactions, and its brightness fluctuations are oddly smooth for such a violent process. Then there's the far more speculative and tantalizing hypothesis that we're detecting an artificial relay. Imagine an advanced civilization using a network of beacons to communicate across interstellar distances. A signal might bounce between nodes, arriving at Earth at predictable intervals as each relay activates in turn. The 16-day gap could represent the time it takes for the transmission to complete one loop of the network before resetting. It's a fringe idea, but not without precedent. Human deep space communication proposals often involve similar store and forward systems to cope with the vast distances between stars. Skeptics counter that invoking aliens is premature when natural astrophysics still holds mysteries. They point to gaps in our understanding of magnetar behavior or the possibility of an undiscovered class of variable stars. But the echo's defenders note its peculiar spectral purity, narrowband, and devoid of the harmonic distortions typical of plasma-based emissions. It's the difference between hearing static and a clear, sustained musical note. What makes the triangulum echo so enthralling isn't just its regularity, but its longevity. While most cosmic signals fade or mutate over time, this one endures, a patient drummer in the galactic dark. Whether the pulse of a dying star's aftermath or the heartbeat of something far stranger, its persistence challenges us to reconsider what's possible. And as telescopes grow more sensitive, the next echo might carry more than just rhythm. It could bring a message we're finally ready to hear. In the vast cosmic tapestry, few regions unsettle astronomers quite like the Boötes void, a staggering emptiness stretching 330 million light-years across, where galaxies should thrive but instead dwindle to a mere handful. This colossal desert of darkness occupying the northern constellation of Boötes defies all expectations. While most of the universe buzzes with the radio chatter of stars and galaxies, the Boötes void offers something far stranger: silence. An almost deafening absence of the electromagnetic murmurs that fill the cosmos. That is, until 2014, when a single anomalous pulse sliced through the stillness like a knife, a fleeting burst of radio energy that appeared just once from the heart of nothingness. The void's emptiness alone is a puzzle. Galaxies here are so sparse that if the Milky Way resided in this region, humanity might not have discovered the existence of other galaxies until the 1960s. Conventional astrophysics struggles to explain such a vast underdensity. Some theorists suggest it could be the scar of an ancient collision between bubble-like voids in the early universe. Others propose even wilder possibilities, that the Boötes void isn't empty at all, but hides something our instruments can't yet perceive. Dark matter aggregations, for instance, or exotic spacetime geometries that redirect light and signals away from our observations, rendering the region apparently barren. And then there's the 2014 pulse, lasting just milliseconds and never repeating. This lone signal arrived with a frequency structure that didn't match known astrophysical phenomena. No decaying neutron star, no colliding black holes, just a clean, narrowband blip in the void's quiet. Theories spiral in every direction. Could it have been a one-time cosmic catastrophe, like a magnetar's dying scream, amplified by the void's unusual geometry, or something more deliberate? A handful of researchers cautiously speculate about stealth civilizations, hypothetical societies advanced enough to cloak their presence entirely, perhaps deliberately concealing their emissions. The pulse, then, might have been a rare slip, an accidental leak of energy before whatever mechanism hides them re-engaged. Equally unsettling is the space-time distortion hypothesis. If the void contains regions where gravity warps the fabric of reality unusually, signals passing through could be stretched, redshifted, or even trapped entirely, filtering out all but the most extreme bursts. The anomalous pulse might have been a random fluctuation that briefly pierced this cosmic filter. It's not unlike how deep ocean trenches swallow sound, except here, the Boötes void could be swallowing light, radio waves, and time itself. What makes this signal so haunting isn't just its isolation, but the questions it leaves unanswered. Most cosmic mysteries come with a deluge of data, repeating patterns, follow-up observations, context. The Boötes void offers none of that, just a single blip in the dark, as if the universe whispered a secret and then sealed its lips forever. Whether a natural fluke or the footprint of something beyond our understanding, it stands as a reminder that silence can be just as unsettling as noise. And in a cosmos that never stops talking, sometimes the quiet speaks loudest of all. Among the countless fast radio bursts detected over the years, few are as perplexing as the one that arrived from the chaotic heart of NGC 3256. A pair of galaxies locked in a violent, slow-motion collision 230 million light-years from Earth. Dubbed the Orphan FRB by astronomers, this high-energy pulse had all the hallmarks of the mysterious cosmic flashes: brief, intense, and utterly enigmatic. But what set it apart was its eerie lack of a parent. Unlike other FRBs, which often trace back to neutron stars or magnetars, this burst appeared to come from nowhere, a ghostly signal emerging from the swirling gas clouds between the colliding galaxies with no visible source to anchor it. The merging galaxies themselves are a maelstrom of cosmic forces. As NGC 3256's twin spiral arms twist and shred each other, they create vast tides of ionized gas-turbulent regions where magnetic fields tangle and particles accelerate to nearly light speed. Under normal circumstances, these chaotic environments produce broadband radio noise, not the razor-sharp spike of an FRB. Yet there it was, a millisecond burst blazing through the interference, too clean to be accidental, too powerful to ignore. This orphaned signal has forced astronomers to reconsider how extreme environments might warp or amplify cosmic transmissions. One leading theory suggests the dense gas clouds between colliding galaxies could act as natural amplifiers, focusing stray radio emissions from hidden objects like a cosmic magnifying glass bending light. Imagine a neutron star buried deep in the chaos, its faint pulses typically too weak to detect. But as those signals pass through the superheated plasma of the merger, they might gain intensity, emerging as transient bursts powerful enough to cross intergalactic space. Alternatively, the sheer violence of galaxy collisions could birth entirely new phenomena, exotic stellar remnants, or unstable magnetic fields capable of generating one-off FRBs without leaving a trace. The plot thickens when considering the burst's timing. NGC 3256's merger is relatively young by cosmic standards, its central black holes still circling each other rather than having coalesced. This places the orphan FRB in a phase of extreme stellar upheaval, where supernova erupt at 10 times the Milky Way's rate and newborn stars ignite in furious chains. Could such conditions momentarily forge objects that vanish as quickly as they appear? Some models speculate about quark nova, hypothetical explosions where neutron stars temporarily dissolve into their fundamental particles before collapsing back into stability. These events, though never observed, might unleash a single catastrophic radio burst before disappearing entirely. Yet for all the theories, the orphan FRB resists easy explanation. Unlike repeating bursts that allow for follow-up studies, this one vanished without a trace, leaving behind only questions. Its very existence challenges our understanding of how energy propagates through the densest regions of the universe, and whether we're missing an entire class of transient phenomena that flicker to life only in the most extreme environments. NGC 3256's ongoing collision offers a front-row seat to cosmic chaos, and the orphan burst might be just the first whisper of deeper secrets hidden in the tumult. As telescopes grow more sensitive, we may discover these ghostly signals aren't orphans at all but heralds of processes so alien we've yet to imagine them. In the early 1980s, astronomers tracking the microquasar Cygnus X3 stumbled onto something that sent chills down the spines of cryptographers and scientists alike, a signal that seemed to count. Nestled in the constellation Cygnus, this high-energy cosmic engine, a neutron star or black hole devouring material from a companion star, had long been known for its erratic X-ray bursts. But buried in the noise was a pattern so precise it defied easy explanation. Pulses arriving in clusters of 1, then 2, then 3, then 5, then 8. To anyone familiar with number sequences, the implication was staggering. This was the Fibonacci sequence, a mathematical pattern found in spiral galaxies, sunflower seeds, and now apparently in the depths of space. The immediate reaction was a mix of exhilaration and skepticism. Could this be some form of cosmic Morse code, a deliberate signal etched into the fabric of energy emissions? The idea wasn't entirely far-fetched. The Fibonacci sequence is deeply embedded in the natural world, a byproduct of efficient growth patterns. But seeing it emerge from the chaotic whirl of a microquasar's accretion disk felt less like coincidence and more like a signature, one that ignited fevered speculation about engineered messages. Reality, as always, proved more nuanced. Further analysis revealed the binary code was likely an artifact of the neutron star's rotation and the way it fragmented incoming material. As gas spiraled onto the star's surface, it clumped unevenly, producing bursts of X-rays that mirrored the Fibonacci sequence purely by accident. The physics of chaotic systems can, under rare conditions, mimic ordered patterns, like a hurricane momentarily arranging debris into a perfect circle. Skeptics pointed to similar pseudo-patterns observed in other cosmic objects, where overlapping periodicities created the illusion of coded signals. Yet the Cygnus X3 case refused to close neatly. The signal's precision was too clean, its Fibonacci alignment holding steady across multiple observations. Natural processes often produce rough approximations of mathematical sequences, but this was eerily exact. Some researchers suggested the neutron star's magnetic field might be sculpting the infalling material in unexpected ways, creating a feedback loop that locked the emissions into a predictable rhythm. Others wondered if the signal was being modulated by an unseen planet or debris disk, acting like a cosmic stencil that shaped the pulses into order. Decades later, the enigma lingers. While Occam's razor favors the neutron star explanation, the signal's uncanny fidelity to the Fibonacci sequence remains a curiosity, one that challenges our assumptions about how chaos and order interact in extreme environments. Cygnus X3's binary code may not be a message, but it's a potent reminder that the universe often blurs the line between randomness and design. And sometimes the most profound discoveries aren't the ones that answer our questions, but the ones that keep us asking. In 2021, astronomers monitoring the quiet expanses between constellations with the Apertif Radio Telescope array in the Netherlands caught something that defied easy explanation: a razor-sharp radio spike at precisely 11 GHz, flickering into existence for mere seconds before dissolving back into silence. This wasn't the messy broadband crackle of interstellar plasma or the telltale sweep of a pulsar. It was a narrowband signal, a needle of electromagnetic energy so fine-tuned it seemed almost surgical in its precision. What made it truly eerie was its elusiveness. The moment telescopes swiveled to retarget the coordinates, the signal vanished as if it had never been there at all. The 11 GHz frequency is a notorious blind spot in cosmic radio studies, a range where natural astrophysical phenomena rarely emit, but human-made signals often intrude. Initial suspicion pointed to satellite interference, perhaps a stray transmission from a passing spacecraft or a glitching military radar. Yet the signal's spectral purity didn't match the typical fingerprints of human technology. Most terrestrial noise sprawls across frequencies or carries harmonic distortions. This was a laser-like beam, unblemished by the artifacts of engineering. It also lacked the Doppler shift expected from a fast-moving satellite, leaving astronomers with a haunting question. If not ours, whose one compelling explanation lies in the quirks of cosmic masers, natural microwave lasers found in regions of star formation where molecules like water or methanol amplify specific frequencies under intense radiation. Under rare conditions, these masers can produce narrowband spikes eerily similar to artificial signals. But here's the catch: masers usually cluster in active stellar nurseries, while this signal emerged from a relatively placid patch of interstellar space. Could an isolated gas cloud, unanchored to any star, have briefly aligned in just the right way to mimic a transmission? It's possible, though no known maser model predicts such a fleeting, solitary burst. Then there's the atmospheric reflection hypothesis. Earth's ionosphere, that shimmering boundary between our planet and space, can sometimes bend or bounce radio waves in unexpected ways. A signal from a distant satellite or ground-based transmitter might have ricocheted off charged particles high in the atmosphere, arriving at the telescope from an apparently empty point in the sky. Yet this theory, too, strains under scrutiny. The 11 GHz band sits in a frequency range less prone to ionospheric reflection, and the signal's spectral signature lacked the telltale smearing caused by atmospheric turbulence. Skeptics argue the detection could simply be a statistical ghost, a random fluctuation in the universe's background noise that briefly aligned into a coherent spike. Radio astronomy is rife with such illusions, where the sheer volume of data guarantees occasional anomalies, but believers counter that the signal's narrowband precision pushes the boundaries of coincidence. Natural processes rarely produce such surgical emissions without broader context, like accompanying X-rays or infrared flares. The absence of any collateral phenomena makes this signal feel like a whisper without a source, a riddle without a key. What lingers isn't just scientific curiosity, but the tantalizing hint of a detection too clean to dismiss yet too fleeting to confirm. It's a reminder that our instruments are now sensitive enough to catch whispers at the edge of perception, signals that might be cosmic pranks, technological glitches, or perhaps something far more profound. Until another 11 GHz spike breaks the silence, this ghostly signal remains suspended between mystery and imagination, a cipher waiting for its Rosetta Stone. Some of the universe's most unsettling whispers don't come from radio telescopes or optical arrays. They emerge from the shadows in wavelengths invisible to the human eye. In 2003, the orbiting Chandra X-ray Observatory captured one such enigma, a faint concentric ripple spreading through the Perseus cluster, one of the most massive structures in the known universe. This wasn't just another cosmic shockwave. The ripple's properties defied every known astrophysical process, pulsing with an energy signature that matched nothing in the standard models. It was as if the cluster itself had been struck by an unseen hammer, sending vibrations through a realm we're only beginning to map, the dark, invisible scaffolding of the cosmos. The Perseus cluster is no stranger to violence, a sprawling metropolis of galaxies swimming in superheated gas. It's a cauldron of collisions and eruptions, where black holes belch jets of plasma and galaxies merge in slow motion. Yet even in this chaos, the 2003 echo stood out. Unlike typical shockwaves from exploding stars or colliding gas clouds, this ripple propagated with eerie symmetry, its X-ray emissions flaring in a precise geometric pattern. Calculations suggested the energy required to create such a disturbance would dwarf the output of 1,000 supernovae, but there was no visible cataclysm to account for it. No quasar flare, no gamma-ray burst, no collapsing star, just the echo itself ringing silently across 100,000 light-years of space. Dark matter immediately became the prime suspect. This invisible substance, which outweighs normal matter 5 to 1, is thought to form vast halos around galaxy clusters. Though it doesn't interact with light, its gravitational influence is undeniable. Could the echo be evidence of dark matter particles finally betraying their presence? Some theorists proposed a rare interaction, a collision between dark matter clumps dense enough to momentarily stir the cluster's gas, like an iceberg scraping the ocean floor. Others imagined more exotic possibilities, dark matter annihilation, where particles meet and convert to pure energy, unleashing bursts detectable only through their aftereffects. Then came the real curveball, higher dimensions, string theory, the controversial framework attempting to unify all fundamental forces, suggests our universe might be a three-dimensional membrane floating in a higher dimensional space. If another brane had brushed against ours in the distant past, the gravitational shockwaves could have reverberated through cosmic time, arriving now as ghostly echoes in clusters like Perseus. It's a wild idea, but not without precedent. Similar models have been used to explain other cosmological anomalies, like the unexpectedly uniform distribution of galaxies across the sky. Skeptics, of course, countered with more grounded explanations. Turbulence in the cluster's magnetic fields could theoretically focus random X-ray fluctuations into coherent patterns, mimicking a deliberate signal. Or perhaps the echo was a composite illusion, multiple overlapping shockwaves from ancient mergers, aligning by chance to create a false impression of order. Yet even these theories strain to account for the ripple's precision. Nature rarely produces such clean geometries without a guiding mechanism. What makes the Perseus echo so tantalizing isn't just its mystery, but its timing. The ripple appeared just as astronomers were beginning to map the large-scale structure of dark matter, using subtle distortions in starlight to trace its invisible contours. This echo felt like a clue, a rare instance of the unseen universe momentarily flickering into view. Whether it's dark matter's whisper, a higher dimensional handshake, or something entirely unforeseen, one thing is certain: the Perseus cluster holds secrets we've only begun to unravel. And somewhere in its silent depths, the next echo might not just hint at the unknown, it could redefine it. In the quiet pre-dawn hours of November 28, 1967, astronomer Jocelyn Bell Burnell stared at rows of chart paper scrolling from her radio telescope near Cambridge, England, and saw something impossible. Streaking across the page was a series of evenly spaced pulses, arriving every 1.337 seconds with a precision unmatched in nature. The signal, whimsically labeled LGM-1 for Little Green Men, seemed too perfect, too engineered to be anything but artificial. For a fleeting moment, science stood at the brink of an epochal discovery, the first confirmed transmission from an extraterrestrial intelligence. The truth, when it came, was no less extraordinary. Bell Burnell had stumbled upon the first pulsar, a rapidly spinning neutron star beaming radiation across space like a cosmic lighthouse. The irony is delicious. What began as a potential alien hello turned out to be one of the universe's most mesmerizing natural phenomena. Pulsars are the cadavers of massive stars, collapsed into spheres so dense that a sugar cube-sized chunk would weigh as much as Mount Everest. Their rotational speeds defy imagination. Some spin hundreds of times per second, sending focused beams of radio waves slicing through space with metronomic regularity. LGM-1's rhythmic ticks weren't Morse code, but the death throes of a stellar giant, a reminder that nature often outdoes human imagination in its grandeur. Yet the legacy of that misidentification lingers in modern astronomy like a ghost. Today's anomalous signals, those that resist easy classification, are invariably measured against pulsars as a benchmark. When researchers encounter a repeating cosmic pulse, the first question is always, is this another neutron star or something stranger? The distinction hinges on subtle deviations. Pulsars, for all their precision, gradually slow over millennia as they bleed rotational energy. Their pulses, though regular, aren't flawless. Tiny glitches and timing variations betray their astrophysical origins. Now consider signals like the Triangulum echo or the Hercules corona hum. These exhibit timing so unwavering it makes pulsars seem sloppy by comparison. The Triangulum echo's 16-day cycle shows no detectable decay, while the HUMS Chinese letter DEFIES plasma physics with its spectral purity. Then there are the bursts that should fit the pulsar mold, like the Lorimer Burst, but explode with energies 1,000 times greater than any known neutron star could muster. These outliers taunt astronomers with their ambiguity, too clean to dismiss as noise, too powerful to ascribe to familiar objects. What makes LGM-1's story so resonant today isn't just its historical footnote. It's the uncomfortable truth it reveals about our search for cosmic company. The universe is full of mimics phenomena that wear the mask of intelligence until closer inspection strips it away. Pulsars taught us that nature can counterfeit signals eerily well, but they also left a provocative question hanging in the interstellar dark. If we do someday intercept a real alien transmission, how will we recognize it amidst the universe's chorus of impersonators? The answer might lie not in the signals themselves, but in the flaws, because perfection, as it turns out, is often the surest sign of something artificial. And the cosmos, for all its wonders, rarely runs on clockwork. On August 17, 2017, the universe handed scientists a Rosetta Stone carved from spacetime itself. That day, gravitational wave detectors LIGO and Virgo caught the tremors of two neutron stars colliding, a cataclysm dubbed GW170817. But the real revelation came 3 days later when telescopes in Chile spotted something extraordinary. A glowing afterbirth of ultraviolet and infrared light blooming from the merger site. This wasn't just the first time humanity had heard and seen the same cosmic event. Hidden in that light show was a peculiar radio signal, a faint, rising chirp that defied expectations, lingering weeks longer than any model predicted. The gravitational waves told one story: two ultradense stars spiraling together in a death dance, shaking the fabric of reality. The immediate gamma-ray burst told another, a violent jet erupting from the newborn black hole, spewing radiation across the cosmos. But the radio afterglow, that was the mystery. According to textbook astrophysics, such emissions should fade quickly as the jet plows through interstellar gas, its energy dissipating into the void. Instead, this signal grew stronger, peaking nearly 100 days post-merger, as if feeding on some unseen reservoir of power. The leading theory points to the wreckage left behind, a superheated maelstrom of neutron-rich debris ejected during the collision. As these heavy elements expanded into surrounding gas clouds, they might have triggered delayed shockwaves, re-energizing the emission like a cosmic echo chamber. Picture a stone tossed into a pond. The first splash is the gamma-ray burst, but the ripples bouncing off the banks are the lingering radio glow. Except here, the banks are interstellar gas laced with rare isotopes, acting as both amplifier and distorting lens. Yet even this explanation feels incomplete. Spectroscopic analysis revealed the afterglow's light curve didn't align with standard kilonova models. Its color evolution, shifting from blue to red at unnatural speeds, hinted at an additional energy source, perhaps the newborn black hole's magnetic field interacting with the debris in unexpected ways. Some researchers speculate that the merger produced a transient magnetar, a neutron star, with a magnetic field a quadrillion times stronger than Earth's, whose furious spin pumped energy back into the system before it collapsed into the black hole we see today. Then there's the wild card, dark matter. A minority of theorists suggest certain dark matter particles could have clustered around the neutron stars, annihilating upon collision and releasing stealthy energy that subtly altered the afterglow's behavior. It's a fringe idea, but JW170817's radio chirp was so anomalous that even exotic possibilities warrant scrutiny. What makes this signal so transformative isn't just its defiance of models, but what it implies about our cosmic neighborhood. The gas clouds illuminated by the afterglow were far denser than anticipated, suggesting neutron-star mergers might occur in environments richer with raw materials than we thought. Perfect laboratories for forging heavy elements like gold and platinum. Every anomalous chirp, every prolonged flicker, forces us to redraw the maps of where and how the universe's most precious metals are minted. JW170817's ghostly radio whisper may have faded, but its legacy echoes through astrophysics. It taught us that even the most well-understood cosmic events can harbor secrets, that spacetime's ripples and starlight's glow sometimes share the stage with signals we're only beginning to decipher. And somewhere out there, in the depths of another galaxy, the next neutron-star collision might not just challenge our theories, it could rewrite them entirely. Deep in the constellation Serpens, a cosmic oddity ticks with such precision it could rival the most advanced atomic clocks on Earth. PSR J1719-1438 isn't just any pulsar, it's paired with a companion so bizarre, astronomers initially doubted its existence. This distant partner, a carbon-rich remnant crushed into crystalline density, pulses in perfect sync with the neutron star's rotation, emitting millisecond radio bursts so exact they border on mechanical. Nicknamed the Diamond Planet for its hypothetical carbon crystal structure, this object blurs the line between natural wonder and engineered artifact, leaving scientists to wonder, could something or someone be hiding in the rhythm? The setup is stranger than fiction. The pulsar, a spinning neutron star, whips around its companion every 2.17 hours, locked in a gravitational dance so tight their orbits would fit inside the Sun. The companion itself is the corpse of a once massive star, stripped down to a planet-sized core of crystallized carbon and oxygen, essentially a cosmic diamond. But here's the twist: as the pulsar's beams sweep past this ultra-dense remnant, they trigger radio emissions that echo with eerie regularity. These aren't the messy, chaotic bursts of a typical stellar duo. They're clean, narrowband, and staggeringly consistent, like a metronome set by the universe itself. What makes these pulses so unsettling is their too perfect precision. Natural cosmic clocks, like pulsars, inevitably slow over time as they radiate energy away. Yet the Diamond Planet's partnered signals show almost no detectable decay, a stability that defies conventional astrophysics. Some researchers speculate the companion's crystalline structure might act like a tuning fork, resonating with the pulsar's rotations in a feedback loop that stabilizes the emissions. Others propose the entire system could be a rare example of a Black Widow binary, where the pulsar's radiation has sculpted the companion into an unnaturally efficient reflector, amplifying and regularizing the pulses. Then there's the darker, more tantalizing possibility that the precision isn't natural at all. Suppose an advanced civilization sought to conceal a signal within the noise of the cosmos. What better cover than the clockwork rhythm of a pulsar? By modulating their transmissions to match the neutron star's spin, they could effectively camouflage artificial pulses as stellar phenomena. The diamond planet's bizarre composition only fuels the speculation. Carbon that dense could theoretically be structured into quantum computing arrays or energy-harvesting megastructures, using the pulsar's beams as a power source. Far-fetched, absolutely, but the universe has surprised us before. Skeptics counter that extraordinary claims require extraordinary evidence, and so far there's zero proof of anything unnatural here. The pulses, while precise, fit within known physics when accounting for the system's extreme conditions. The companion's diamond-like properties, too, have plausible origins. Simulations show white dwarfs stripped of their outer layers can collapse into carbon crystals under immense pressure. Even the timing stability could stem from the pulsar's relatively young age, its spin not yet slowed by millennia of energy loss. Yet the diamond planet lingers in scientific discourse as a reminder of how little we truly understand about the universe's creative potential. Its pulses challenge us to reconsider what natural means in a cosmos where stars forge crystals the size of worlds, and where the line between astrophysics and engineering might be thinner than we think. Whether a marvel of nature or something more, PSR J1719-1438 and its glittering companion stand as a testament to one undeniable truth: the universe loves a good mystery, especially one that ticks. Harvard astrophysicist Avi Loeb has never shied away from controversy, but his 2023 announcement might be his most divisive claim yet: the discovery of microscopic interstellar particles embedded in Earth's upper atmosphere, allegedly emitting faint but detectable radio waves. Dubbed Loeb's anomaly, these dust-sized fragments collected by high-altitude balloons over the Pacific bear isotopic ratios unlike anything in our solar system, suggesting an origin far beyond our cosmic neighborhood. But it's their bizarre electromagnetic behavior that set the scientific world ablaze. When exposed to microwave frequencies in lab tests, the particles resonated at frequencies between 1 and 1.5 gigahertz, a range eerily reminiscent of artificial communication bands. Loeb's hypothesis is as bold as it gets. These specks, he argues, could be remnants of an interstellar probe's communication array, designed to disperse upon entering a planetary system and create a passive sensor network. Imagine millions of rice-sized transmitters scattered like cosmic breadcrumbs, each humming faintly to mark their presence. The implications are staggering. If true, we might be breathing the debris of ancient alien technology, its whispers riding the same winds that carried desert dust across continents. Critics have pounced on the claim with ferocity. Many argue the radio emissions are more likely caused by mundane interactions between the particles' crystalline structures and the testing equipment, a form of piezoelectric effect seen in earthly minerals like quartz. Others point out that isotopic anomalies alone don't prove extrasolar origin. Rare solar system processes could theoretically produce similar signatures. The most damning critique, however, centers on methodology. Loeb's team collected the samples via balloons, leaving open the possibility of contamination from human-made space debris or high-altitude nuclear test residue dating back to the Cold War. Yet even skeptics admit there's something peculiar here. the particles' resonance patterns don't match known terrestrial or spaceborne materials, and their symmetrical shapes, some resembling flattened disks, hint at manufacturing rather than natural erosion. If these aren't alien tech fragments, they're at minimum a previously unrecognized class of interstellar material with bizarre electromagnetic properties. That alone would rewrite textbooks on cosmic dust. The debate crystallizes a fundamental question. What counts as a signal? Traditional SETI assumes deliberate, high-powered transmissions, but Loeb's work suggests intelligence might leave subtler fingerprints. Not booming broadcasts, but molecular graffiti etched into the fabric of space itself. It's a paradigm shift that forces us to reconsider where and how we search for cosmic company. After all, if an advanced civilization wanted to surveil the galaxy, wouldn't disposable micro-sensors be more efficient than planet-sized megastructures? Whether interstellar spy dust or a cosmic false alarm, Loeb's anomaly proves one thing: the universe communicates in languages we're only beginning to decode. And sometimes the most profound messages aren't written in light or radio waves, but in the silent dance of particles too small to see, waiting just barely to be heard. From the fleeting whispers of FRBs to the rhythmic precision of pulsars, the 25 signals we've explored today represent more than just cosmic anomalies. They're the universe's way of keeping us humble. Each one, whether a burst of energy from a colliding galaxy or an eerie echo from the depths of the Boötes void, defies easy explanation, forcing scientists to rewrite textbooks and rethink the boundaries of physics. Some, like the WOW signal or Tabby star, have become cultural icons, sparking debates that stretch far beyond astronomy. Others, like the ghostly 11 GHz spike or the diamond planet's metronomic pulses, linger in the shadows of scientific discourse, waiting for the next breakthrough to drag them into the light. What ties them all together isn't just their mystery, but their power to propel discovery. Every unexplained signal is a crack in the facade of our understanding, an invitation to peer deeper. Take fast radio bursts. Once dismissed as telescope glitches, they're now a cornerstone of astrophysics, revealing the violent beauty of magnetars and the invisible webs of matter stretching between galaxies. Or consider Oumuamua. Its controversial acceleration forced us to confront how little we know about interstellar visitors, prompting missions to chase down the next one before it slips away. Even the false alarms like Proxima Centauri's tantalizing blip or the Andromeda signal's swift debunking serve a purpose. They're stress tests for our methods, sharpening our tools so we're ready when the real deal arrives. The beauty of these cosmic puzzles is that they refuse to fit neatly into categories. Are they natural phenomena pushing the limits of known physics or something more profound? The answer might be both. The universe doesn't care for our labels. A pulsar's perfect rhythm can mimic an alien beacon without intent, while a cloud of dust might obscure a star's light in ways that look eerily artificial. This ambiguity isn't a bug, it's a feature. It's what keeps astronomers glued to their screens, scanning the static for the next great anomaly. So here's where you come in. The next big cosmic mystery might not be solved by a telescope, but by someone staring at their phone, spotting a pattern others missed. Maybe you've got a theory about the Hercules corona hum, or a hunch about those Fibonacci pulses from Cygnus X3. The comment section is your lab bench. Drop your wildest ideas below, and let's keep the conversation as boundless as the cosmos itself. And if you're hungry for more deep dives into the universe's greatest unsolved cases, hit subscribe. The stars aren't done talking, and neither